Well, good afternoon, everyone. My name is Clark Yuan, and today I will be talking to you about how the US military and some of our allies are starting to increasingly use LiDAR, photogrammetry, drones to support operations, maintenance, and planning on the modern battlefield, and how specifically this is going to be changing the spheres of influence in both INDOPACOM and also in the European Command. A little bit about my background. I was a former Army intelligence officer. I commissioned from the US Military Academy at West Point in 2012. Served 7 years as an intelligence officer in mostly the Indo-PACOM theater of operations in South Korea and also in Washington State. After I left active duty, I was an innovation officer for 4 years, looking at capability gaps across the military intelligence spectrum. And currently, I'm the founder and CEO of Stitch3D, which is an Air Force-backed software company that supports visualization and sharing of point cloud data and rasters. So the current geopolitical state of the world has changed quite a bit over even the last 5 years. I left active duty in 2019, and when I left active duty from South Korea, one of the biggest questions on our mind was how do we defend US interests and our allies in the Indo-PACOM theater of operations with increasing asymmetrical capabilities coming out of China. As you can see here on the map, a lot of our bases are clustered around this island chain, which, as many of you probably know, there's kind of this first and second island chain stretching out from China that but it's meant to kind of support operations within a blue water navy from China going into the rest of Indo-PACOM freely. However, this is no longer really the reality of today, because now we're looking at capabilities coming out of China that's asymmetrically preventing us to be able to execute our operations. Aircraft carriers can no longer sail freely, given the intercontinental ballistic missiles, and also the short-range missiles even coming out of China. So the military has had to increasingly change our paradigm of operating in this theater, and this is also similarly true as we look at Europe as well. The new paradigm the military is shifting towards is something called ACE, the Agile Combat Employment. And basically what this is we're no longer operating from centralized commands, now we're operating distributed commands. So now, instead of moving forward as brigade operations and brigade combat teams, we're increasingly moving forward in company commands and battalion commands in terms of the size of the movement and the maneuverability of the elements. What this looks like is now there's this hub and spoke operational method where you have a continuation effort within like a centralized base in Korea or Japan or in Guam or in Hawaii, and you have all these different spokes around that operation. And where we're taking this operation now is looking at opening up some of the World War II islands that we had in the South Pacific and making those contingency operations of efforts for air-based operations and for contingency flights. So what this looks like is the base there, the hub, might be Andersen Air Base at Guam, or it might be Yokota Air Base in Japan, or Osan Air Base in South Korea. And then some of the spokes would be Tinian Air Base in the Northern Mariana. And actually, that's the first spoke that the Air Force is opening up to kind of support this new paradigm of ACE operations. Really what this means, though, is that this is a massive geospatial effort in order to open up these old World War II air bases. So this is where Tinian is. It's about 300 kilometers north of Guam. And after World War II, it looked like this. It was an fully operational air base. And now it looks like this. It's been completely overrun by the jungle. And so in order to rapidly clear this island and recover some of the airways, this has become a massive geospatial and terrain analysis problem in order to go out there and clear the trees, flatten the airfields, and make it operational again. The Air Force has invested a lot of money and efforts to make this geospatial problem a reality. So now they're contracting general contractors to go out there and survey the land, clear the trees, bring in the bulldozers, and start to level out the fields. One of the runways that we scanned here has been basically assessed for levelness. So when we look at how the airfield pulls water after it rains, you can start to see where the elevation is. So this is one of the ways that the Air Force is using LiDAR to do terrain analysis. Another one, of course, is doing cut-fill volume calculations. As many of you probably saw with Ukraine, airfields are one of the most important infrastructures at the beginning stages of combat. So anytime an airfield is attacked, we need to quickly do an operation what's known as RADAS, Rapid Airfield Damage Assessment. And what that means is going out there and assessing the volumetrics of the cratered runway and figuring out which holes we need to fill in first in order to create that minimum viable airstrip for the fighter jets to take off and defend the airspace. Again, this is a problem that the Air Force can use LiDAR for. They can quickly survey a cratered runway using drone LiDAR, and then calculate volumetrics for each one of those craters individually, and assess which ones to fill in first and triage. The problem, though, is that, as many of you know, point cloud data, rasters, orthos, all these data sets are very complex and large, and they're not easy to share. So what you have is you have an engineering unit out in the field that's doing a lot of the data collection, but they're not doing the assessment. So after they collect the data, they need to ship it off, typically in snail mail on hard drives, or in the case of the military, on Blu-ray DVDs, to a higher organization that's actually doing the analysis. Now, this could be the Army Corps of Engineers, it could be a civil environmental engineering unit, or in this case, it could be the Air Mobility Command, the A5 planning unit, or the Air Force Civil Engineer Center. These units then do the analysis for whether it's leveling, whether it's crater volumetric calculations, whether it's assessing tree height or tree obstruction across an imaginary airspace surface, and then they send those reports back to the operational unit to actually go out there and conduct the operations. This entire process can take anywhere from 3 weeks to over a month. And so as you can see, there's very slow turnaround times on some of these geospatial operations, which is honestly not very acceptable when you have a theater of operations that's moving so quickly. So just looking at a case study here, the Air Force, like I mentioned earlier, has funded our company to do R&D to create a cloud-native platform to build out a secure platform to quickly share this data over a cloud environment. And we start with Joint Base Lewis McChord, which is the primary, we call it CONUS, the Continental US Air Base, supporting theater of operations in the PACOM theater. Now, the major problem that Joint Base Lewis McChord, or McChord Airfield, faces is tree obstruction on its airfield. So in the Pacific Northwest, you have these conifer Douglas fir trees that can grow up to anywhere from 150 to 250 feet tall. And what happens when that happens is the trees actually start to grow so tall that they penetrate the imaginary airspace surfaces on a runway. When this happens, the Air Mobility Command, the A5, has to raise the instrument landing system minimums to ensure safe operations and safe landing for approaching and landing aircrafts. Now, as they raise the instrument landing systems, this means that the aircraft has to descend at a steeper rate, which is putting the aircraft and the crew at more risk. Now, JBLM has not had a drone LiDAR survey in the last 5 years. So when we went out there to do this operation, we actually took a drone out there. And the reason why it takes usually 5 years to do a LiDAR survey is because they typically do it with a fixed-wing drone. The command at JBLM wants to explore now how they can use drones to increase the frequency and the continuity of basically doing drone operations to LiDAR the surfaces whenever it's needed instead of every 5 years. So after we collected the LiDAR data using a free fly system, which in the US, most of the drones have to be NDAA compliant, we upload the data to Stitch3D, which is just a cloud-native platform, to host all this data. We created a project, uploaded 3 point clouds and 8 rasters for the DEMs and the orthomosaics into the platform. And then this allows the Air Force units to quickly share that data out from the engineering units to the higher commands. For this project, the data needed to be shared with the Air Mobility Command, the A5, as well as the AFCAC, which is the Air Force Civil Engineer Center. If you all want, you can scan this QR code to actually see what this data set looks like on your phone. And this just facilitates the ease of how quickly you can share that data out. Now, what you're seeing here is actually 2 separate scans. One of the south approach, and then one of the north approach. The south approach is about 750 acres, and then this one is about 170 acres. So one of the things the Air Force needs to do is to be able to ground classify the terrain, and then look at the obstructions in an isolated format. And then once they do that, they can drop annotations, create critical incidents. For this situation, it's the trees. And then they can start to mark the trees down as whether or not it's obstructing the airspace. This might sound silly, but the reason why this is important is because Washington State has very strict environmental laws. So you can't just go out there and cut down every single tree. Each one has to be marked individually, geo-referenced to a specific location, and then given to the forestry department to then go out there and cut down trees individually instead of just cutting down the entire forest. So here you can get the lat long, the X, Y, Z information directly for each offending tree, and then give that over to the forestry department to figure out which trees to cut down. All right, and then so what you're seeing here is also a sample use case of the cut fill crater volume calculations. For this is going to be a fill, but this is how easily the Air Force now can do cut fill operations on a crater runway. They simply draw a perimeter around it and then figure out the base plane methodology they want to use and then what material they want to fill that crater with. And now I can easily get the cost and the weight of the imported material that needs to come in to fill that crater up. The other thing here that we're looking at is the glide angle. So whenever you're looking at a tree obstruction, it's in reference to that imaginary airspace surface that Air Mobility Command has specified for the safe landing of that airfield. So that way you can draw a glide angle out and see which trees are offending. Another tool the Air Force has been using is just the height profile. This is a pretty standard tool for assessing the quality of the point cloud, but for this specific use case, they can also quickly get a horizontal profile view of which trees might be in offense. Now all of this data is geo-referenced to local state plane, so that means you can turn on the base map and see exactly where in the world it is. This is in Washington State, but if you were operating out in Tinian or in the South Pacific, this would be very helpful to basically align all the engineers and all decision makers onto one coordinated map. And then you can toggle off the point clouds to see where exactly those trees are in relation to a base map. Moving on to the raster side, so you can just switch over from the 3D view to the 2D viewer. These are the elevation models that were generated from that point cloud for the hillshade DEM, the slope DEM, the elevation DEM for McCord. And this is useful when they're trying to look at terrain flatness. So when they're laying out a new airstrip, they're basically looking at the elevation overlays with the orthomosaics to figure out where exactly the best new location would be for an airfield would be. So again, all this data can be now shared out via a simple QR code or a web link, and it travels together as a package, which is a lot easier and faster than shipping hard drives, because it aligns all the decision makers together in a much more unified way. So the end result is once all this data is sent up to AMC A5, Air Mobility Command, they overlay that CAD model, the DWG drawings for the airspace surfaces, with the offending trees, and they can quickly see here which ones are critically obstructing the airspace surfaces and which ones are encroaching. They give this data over to the forestry department with each individual trees marked down in an Excel file, and that's essentially what the forestry department uses to go down and mark the trees and cut down the trees that are violating the airspace. So with that, I'll be standing by for any questions.